Hello, my name is Matt Klein and welcome to this engineering taster session. Hopefully you caught my contact details, my email address at the beginning of this video, so do feel free to contact me if you have any queries on this video. So in this engineering taster session we're going to be building some very simple circuits on a prototype board, or the slang or nickname for that is a breadboard. We're going to be using a formula you may remember from GCSE, known as Ohm's law, to make some predictions about the relationship between current, voltage and resistance in this simple circuit. And then we'll have a go at actually measuring the current, voltage and resistance using a multimeter, this device here. Okay, so let's get started. So in this breadboard, you can't see it, but we have some horizontal, underneath this plastic, we have some horizontal copper tracks, and we can push wires into these holes to connect to the copper. So we have two horizontal ones here, which is separate, two horizontal ones over on the other end, which also conduct horizontally, and we have lots of vertical copper tracks. There are gaps, so there is a gap between the horizontal rails at the top, and the vertical ones conduct this way. There's another gap in the middle, then another one which conducts, and another gap here. So we want to build a complete circuit. So what we do is we connect the positive terminal of our battery, which is normally the red wire, to the top rail, and we connected the negative, the black terminal of the battery, to the bottom rail. And so to complete the circuit, we just need to plug components into the breadboard, bridging over these gaps. So the absolute simplest circuit we could do would be to take a resistor. So here's a resistor. You can see some values on it there. And if I connect that to the top rail, the positive rail, and the other leg of the resistor all the way over to the bottom, I've now bridged all of these gaps, and we actually have a complete circuit. So as I said, you can imagine positive charge flows out of this positive rail. This would be called a conventional current, along this red wire, through the resistor and back. So that should actually be conducting now as we speak. Okay, so let's make a prediction for this circuit, and let's start with checking the resistance of our resistor. So as we can see, the nominal value is 100 ohms. It says 100R, and it says 10%. So let's pause the video here and just think about what this 10% tolerance means. This 10% figure is a tolerance as stated by the manufacturer. So they're saying that this is a 100 ohm resistor plus or minus 10%. So what's the biggest value this resistor could be, and what's the smallest value this resistor could be? Okay, so of course the biggest possible value would be 110 ohms, and the smallest possible value would be 90 ohms. So let's measure it with our multimeter and see what it actually is. So using the multimeter here, what we do is we check that our red probe is connected to ohms. So down here we can see volts and ohms, so we're good to measure ohms for resistance. The black probe is on common, you always plug into that. But we will need to swivel this dial round to ohms. So if we're expecting a 100 ohm resistor roundabout, we shouldn't need more than 200 ohms, so we'll connect down there to 200. And now we put the two probes over the resistor, and it's saying 98.8 ohms. So that's very close to 100 ohms. So let's just write that down. So let's round that to 100 ohms. So the resistance of our resistor is 100 ohms. Okay, I'll put that back into the circuit as it was. Before I complete the circuit, before I plug that other leg in, we should also check the voltage that we're getting from this battery. Now, unfortunately, I'm using some old kit at home here, which does have a few issues, and I think this battery is starting to run a little flat. So let's check how many volts we're getting from this battery. I'm going to put the dial here round to DC volts. I know I'm not going to be getting more than 20 volts from this battery. So 20 volts there, we can read up to a maximum of 20 volts. The red probe is plugged into volts still, so we can also measure volts using this socket. And I'm going to touch the red probe to the top rail, the positive terminal of the battery, and I'm going to touch the black probe to the bottom rail, and that's saying 4.8 volts. So let's make a note of that. The voltage from our battery is 4.8 volts. I'm going to round it to 5 volts. Okay, so finally, how could we predict the current that is going to flow once I close the circuit and plug this resistor back in like so? How much current should be flowing through this 100 ohm resistor with 5 volts across it? So for that we need Ohm's law, which you may remember from GCSE. So Ohm's law is this formula: V equals I times R. Voltage is current times resistance. So the voltage dropped over the resistor is equal to the current that flows through the resistor times the resistance of the resistor. Of course, voltage is measured in volts, current is measured in amps, and resistance is measured in ohms. We're interested in this I, which is the symbol for current. So we need to rearrange this formula now and make I the subject of this formula. So again, over to you. If you pause the video here, see if you can make I, the current, the subject of this formula. So we have I equals something. So we need to divide both sides of this formula by R. So what we get is voltage divided by resistance is current. V over R equals I. So we can plug some numbers into this. We said our voltage is round about 5 volts. Our resistance is 100 ohms. Again, roundabout. So we're going to get here 0.05 amps. So what would be nice would be to verify this, to take a third and final measurement using our multimeter to see what current is actually flowing through this resistor. Now unfortunately I know that I have blown the fuse in this multimeter, so at the moment it's not able to measure current. You simply won't get a number on the top. This is quite an easy mistake to make if you short circuit something, but I can show you how this would be done. And measuring current is a little bit more tricky than measuring voltage or resistance, which we've done already. So if I think the current is going to be in the order of milliamps, then I can leave this red socket where it is, because it does say milliamps down there. If I'm going to be measuring a bigger current up to 10 amps, then I would need to move this red socket up to the top where it says 10 amps. But we're expecting 0.05 amps, so we could leave it down there. We will need to rotate this bezel round to amps over this side. So 200 milliamps down there would be a good setting. And very importantly, there's a fundamental difference on the breadboard, on the way that you take the measurement. So when we measured the resistance of our resistor, we simply put the probes over the resistor, like so. We did that. We put the probes over the resistor to measure resistance. And we did the same thing when we measured voltage. When I measured the voltage from the battery, we put the probes over the battery, across the rails. So these are parallel measurements when you put the probes over the component. This is not how we measure current. To measure current, we need to break the circuit. So if we want to know the current through the resistor, we need to unplug one leg of the resistor, and then we take our multimeter, behaving as an ammeter, and insert it into that gap. So what I would do is place the black probe down here on the bottom rail, just touching that bare bit of metal on the end of the black wire, and I connect the red probe to the resistor like so. So the current is flowing through the resistor into this red probe, through the multimeter, and from this black probe down to the bottom rail and back to the battery. So we're inserting the multimeter into this gap and using it to complete the circuit. So we're forcing the current to flow through the multimeter. As I said, unfortunately there's no value here on the multimeter. It's not giving us a current value at the moment. Okay, so that is a very simple circuit with just a resistor, but we've made predictions of current, voltage and resistance, and a couple of those values we've measured with the multimeter. What if we were to introduce another component, perhaps an LED? Let's take an LED. A light emitting diode. Now, an LED does not obey Ohm's law. So that formula we just used, Ohm's law, can be plotted on a graph, a current voltage graph. As so. That is supposed to be a straight line. So Ohm's law says that provided our resistor or our component which is obeying Ohm's law, providing its resistance stays constant, which would usually mean that its temperature must remain constant, then the current is directly proportional to the voltage. If I was to double the voltage over my resistor, I should also double the current. But an LED does not obey Ohm's law, and its graph is not so straightforward. First of all, we have a threshold voltage. We have a minimum voltage which we must hit in order for any current to flow. If we're below this threshold voltage, let's put a VT, the threshold here. If we're below this, there will be no current, or virtually no current. Once we reach that voltage, the current will rise up exponentially. Now this threshold voltage does vary and does depend on the colour of the LED. Now for a red LED like this, the voltage is often around 1.8 volts. Another important difference about an LED, unlike a resistor, is that it does have a polarity. A resistor does not matter which way round you plug it in. You can unplug it and turn it around, swap the legs round, and the current through it will be the same. It conducts exactly the same way, forwards and backwards. That's not the case for an LED. If we look closely, we can see that one leg is longer than the other. This long leg is the positive leg. So the long leg, if I put my LED in series with this resistor now, I must make sure that the long leg goes up to the positive rail. The long leg must connect to the positive rail and not the other way around. So, how could we predict the current that is now flowing in this circuit? Well, as we said, we cannot use Ohm's law on the LED. We can only use Ohm's law on the resistor. But we know that if this LED is on, it should be dropping around, let's round this value to 2 volts. We said the battery is providing 5 volts. So I'm going to ask you to pause the video in a moment to make a prediction about how many volts remain to be dropped over the resistor. If there's 5 volts available from the battery, 2 volts are being dropped by the LED, then how many volts must be dropped by the resistor? And could we then use Ohm's law on the resistor to predict the current through it? Before we do that, let's draw a circuit to help ourselves to compile all of this information together. So we have a battery which is giving us approximately 5 volts. An LED, and a resistor. So the battery is providing 5 volts. The LED should use around 2 volts once it's conducting. So how many volts must be dropped over the resistor. And how would we now use Ohm's law to predict the current that flows in that resistor? So pause the video and have a go. Okay, so we will return to Ohm's law, which says V equals IR. We need to rearrange this formula again, so we get I equals V over R. But we can only use Ohm's law on the resistor, which means the resistor must be dropping round about 3 volts. There's 5 available from the battery, the LED drops 2, the resistor must drop the difference. So 5 minus 2, which is 3, and its resistance is still 100 ohms. So we will get around 0.03 amps flowing through our resistor. Unfortunately, as I said, we're not able to measure current with a blown fuse on this multimeter, but we can have a go at measuring the voltages. So I need to make sure that this dial on the multimeter is around here on DC volts. Let's check our battery is still giving us 5 volts, because I'm a little bit dubious about that. 4.5. Okay, let's put the resistor back in. Okay, well, I had to pause the video there. I think the battery, although it's still outputting 5 volts, you can see that is quite a bit less than the 9 volts it's supposed to output. And as soon as we try and draw a current from this battery, its internal, when a battery goes flat, its internal resistance grows. And this is quite a small resistor, 100 ohms is quite small. So the battery is no longer able to take much load, and the current that we're trying to draw from it, because of this rather small resistor, we're trying to draw quite a large current here, and the battery can't handle it. And the LED only lights for a very brief second. Anyway, we can still check that the LED is actually conducting. It shows 1.5 volts across it, which is a little bit less than the 1.8 volts that I said is typical for a conducting LED, but that's okay. The 1.5 volts across the LED there is also quite typical. So that concludes this engineering taster session. Hopefully I've inspired you to perhaps go away and try and build one of these circuits for yourselves. So we've looked at how to build very simple circuits on the prototype board. We've made predictions for what should happen in our circuit using Ohm's law to relate current, voltage and resistance. And we've had a go, not all that successfully, at measuring current, voltage and resistance with the multimeter. All of this equipment is actually rather cheap, rather readily available. Now that the shops are beginning to open again, you can buy little kits like this for not very much money at all in shops such as Maplin's, or you can buy these kits online somewhere like Amazon. Do contact me. I gave you my email address at the beginning of the video. Do contact me if you have any queries on what you've seen today, or would like to seek some advice. Thanks very much. Bye bye.